All right, when we are back and we're going to go through our lecture 12, root locus. And root locus method is a very, very important basically technique, and it's a graphical method and to examine basically how the roots or the poles of our closed loop transfer function will vary as a function of our gain. It's really, really useful for control design, and especially because the closed loop poles determine essentially our stability of our system. So we're going to apply the root locus method. The key aspect of when you're doing root locus, our characteristic equation, our transfer function, has to be written in this format. And this form is really, really essential. So sometimes we're going to need to basically algebraically manipulate it. And we need to basically be careful with this. You'll see some other courses, this L of S is just a generic form. It is not the open loop transfer function necessarily. So we'll get into the nuance of that in just a second. So let's look at an example. So simple unity feedback control system. This is our plant. This is our controller. So first order, we know it's stable with a pole here. Proportional controller here. We know that the closed loop transfer function will be Cp over 1 over C times Ps. And what we see is we're in this kind of form, right? Where it's K times some transfer function. So this is what it looks like. So our S, essentially, we see as K increases to infinity, our pole moves to negative infinity, becomes increasingly basically fast and positive and stable. So let's examine this a couple ways. So we know, for example, if I have, actually, let's go ahead. Where's my transfer function? And let's go ahead. I'm going to just shift enter this for our critical functions. I want to be able to manipulate like this as well. So for example, we're going to actually, let's take this here. I'm going to bring it up here. So C of S is this is S plus 1. So our G of S is this. This is our G of S for the transfer function. C of S, let's make sure. Be careful about that. That's going to be our G of S. And now we can just manipulate. And it's not liking that we don't have evaluation. Can we do dynamic updating enabled? There we go. So now we can see. So this is basically as we change K. So as we change K here, I wonder what's. And then let's just do GS full simplify. Oops. We can take this. There we go. And we can see now what we've got. So as we increase K, we know that basically we're going to start to shift, right? And it's just going to shift more and more and more as we increase to basically minus infinity, right? And you can see there's some little shift here. If we actually simplify that G of S, I'm going to say GS simple. There should only be one pole in that system. GS simple. We're at 0. Oh, ooh. What don't you like? We need transfer function model, S. Yeah, here we go. So now we can visualize this. Sorry about that. But it's fun to see, at least to me. So as we increase this K, we just move the pole to minus infinity. So we can visualize that ourselves, but one of the cool things that we can do, and make sure you can see the same thing here, I'm just putting the transfer function like that. You see that we had that weird issue with if we didn't simplify essentially the g of s. That's one of the weird things that you'll see a little bit in Mathematica, so be careful about that. Always use your intuition. But instead, we can write our L of s, which is just written as k times s over s plus 1. So we can write out that L of s that we've defined, and we can use a built-in function in Mathematica, which is the root locus plot. And you can see the root locus plot. It's showing you essentially, if I have, you see where that x is? This is my starting point. And what it's showing in the blue line is as I increase k, so for example, if I just do k from 0 to 5, right, I'm not reaching, basically a value of -6 yet. And that's, unfortunately, it's hard to kind of see the values. And actually, you can see here, this would be my value of k equals 2.5. And you can see where essentially the pole shifts. And it's not liking this because it's not liking that. Actually, I'm going to just do 500. It's not liking it because my dynamic updating. So it's giving us a headache. If we did it to 50, right, you can see more of where essentially they're going. But that blue line is showing you, and it's for this specific pole, how it's going to move as we increase or change k. So that's really the key idea here in this scenario. So root locus is a cool way to see and visualize how the poles will effectively move. So pretty straightforward. I mean, it's things that we've done before, but now it's a new tool that we have at our disposal. And we can essentially see the pole behavior. Here, as it increases move leftward on the real axis, never becomes complex, and we see essentially that response. Faster response, basically, again, kind of that quicker behavior effectively. So next time we're going to do a more complex system just to kind of see how some different poles may move, and then we're going to develop some rules for how we can predict essentially that pole motion. So we'll see you next time. Thanks. Bye.